This is a very short video in which I want to walk through some simple exercises involving dot product. So we're going to take vectors u, v, and w. U is 2 minus 2, v is 5, 8, and w is minus 4, 3. And we're going to work through a, b, c, d, and e. All right, the first is just u dot v. So let's make sure we can evaluate a dot product. In this case, we have 2 minus 2 dotted with the vector v, which is 5, 8. So we multiply the first two entries together. This gives us 2 times 5, and then minus 2 times 8. And so this gives us minus 6. That was easy. Now let's look at b. U dot v and then w. So the first thing I want to point out is that when we do u dot v, as we just did, we get a scalar. So what we're really looking at here is a scalar times a vector. So this is going to be minus 6 as a scalar times the vector w. And so we need to multiply minus 6 times all of the entries of w. So the answer here is not a number, but is a vector. It's minus 6 times minus 4. So that's 24. And then we have minus 6 times the second entry of w, which is a 3. So that gives us a minus 18. Okay, so in the first exercise we got a scalar, but in the second exercise we got a vector. Next we're going to look at u dot 2 times v. So here we're going to be taking another dot product. Now we're taking the dot product of 2 minus 2, but times the vector 2v, not v. So before we do that dot product, we need to multiply every entry of v times 2, because this is the scalar 2 times the vector v. So we're dot producting with the vector 10, 16. So now we just have another normal dot product to evaluate, and this gives us 20 minus 32, giving us an answer of minus 12. Problem D is the length of w squared. So for this, we're going to have the square of the square root of the entries of w all squared and added together. So minus 4 squared plus 3 squared goes under the radical. That would give us the length of w, but then we square everything because it's the length of w squared. So this is 16 plus 9, which is 25. The length of w, by the way, is 5. And then lastly, we have u dot v minus 2w in parentheses. So let's split this up into two calculations. Okay. So first let's look at v minus 2w. This is a linear combination of vectors. And it's going to be the vector v, which is 5, 8, minus 2w. So minus 2 times the vector minus 4, 3. So following this linear combination, we should get 5, 8. And then minus 8, 6. We add those vectors together, and we get 13, 2. Now we need to take the dot product with u. So this dot product, u dot v minus 2w, is the dot product of 2 minus 2 dotted with the vector that we just produced, 13, 2, giving us 26 minus 4, so 22. Now, something I want to point out is that this is not the only way to answer this. So let's solve the same problem in a different way. I'll use the color red for the next way of solving it. So let's use some of the formal properties that arose in an earlier video. So u dot v minus 2w can equivalently be written as u dot v minus u dot 2w. And in fact, we could also take that 2, the scalar, and put it outside the dot product. This is also equivalent to u dot v minus 2 times the number u dot w. And as you work through this, you should check with yourself that all of this makes sense, that we should be ending up at the end of this calculation with a number, because a dot product will give us a number, and a dot product will give us a number, multiplied times a number will give us another number, and when you subtract them you get another number. So let's use this last one to calculate this, and we see that this is equal to, well, u dot v we already calculated before, But let's all write it all out. So 2 minus 2 dotted with 5, 8. And then we have minus 2 times u dot w. So 2 minus 2 dot w minus 4, 3. So we have here again our 10 minus 16 giving us the minus 6 that we calculated in A, minus 2 times the u dot w. So minus 8 minus 6 producing minus 6 plus 28. So again we get the same answer of 22.